This is lecture 19, and we're going to be talking about hypothesis testing today. So this is going to start to really feel like a statistics class, but now we've built up kind of most of a semester of theory, and we can really get into kind of hypothesis testing in a real kind of advanced way here. So we should start off with a definition of what a hypothesis test is, or what a hypothesis is. So our first definition is, let's say, a hypothesis. And for the sake of kind of mathematical statistical hypothesis testing, a hypothesis is a statement about a parameter. That's all as mathy as we're going to get with that. Typically, it's going to have two kind of joined statements. One, H naught, which we're going to call the null hypothesis, is that our unknown parameter lies in some set we're going to call big theta naught. So H naught is called the null hypothesis. And it is that our unknown parameter lives in some set theta naught. And our alternative hypothesis, the alternative to the null, denote HA for alternative, is that our unknown parameter theta lives in some other set, call it theta A. That will be our alternative. So a hypothesis is basically a statement of one statement, the null hypothesis, versus another statement, the alternative. They concern where our parameter lives, the unknown parameter lives, right? So we collect data. We don't know what the true underlying distribution is. It's parameterized by some parameter theta. And theta can live in some space. It could live in part of the space called theta naught. And the hypothesis that lives in that part is called the null hypothesis. Or could live in another part of the space, call it theta A. The hypothesis that lives in that part of the space is called the alternative hypothesis. The constraint here, or there are kind of two constraints here, which is one, that theta naught intersect with theta A better be empty. If not, it's going to be hard to determine which of these two is more likely, because you could end up with certain parameters living in both, and they could both be true. So we don't want them both to be potentially true or likely. So we assume that you're in one or the other, but not both. And two, you have to be in one of these. So the whole space of possible parameters, theta, is the union of theta naught and theta A. Now, that's not this. The first condition is a real condition that no one particularly has any desire to violate. The second one seems like it's maybe some constraint, but it's not really that big a deal. We're just basically defining the space. One way to see it is you define your null hypothesis, your theta naught, you find your alternative, big theta A, and then you say, okay, the space where I can live is just the union of those two things. So sometimes that's one space or another space, but basically we're defining the space of possible values for our parameter as the union of these things. Another way to say this, you might have seen here, is that let's say theta naught and theta A, they partition space of possible parameters. So equivalently, you could say that theta naught is the space of possible parameters theta less theta A, or theta A is theta less theta naught. They're complementary with respect to the total space. So you're in one or the other, not both, and you have to be in one or the other. Okay. We can look at some examples of this. Let's assume that theta is the proportion of defective items so that theta is some number, so that little theta is in big theta, which is just the set 0 to 1, right? So you can imagine some manufacturing process. You manufacture things, then you do some testing of them. Some of them will be defective, some of them won't be. Or maybe you ship out cars, some of them will need to be recalled, some of them won't. Some of them have a defect, some of them won't. So the proportion of those, let's call that theta, little theta. And that little theta lives in our set of all possible proportions, which is just that unit interval. What we might do, we might, for example, test maybe a null hypothesis that, let's say that theta, that our defectives is less than 1 in 10 defectives versus an alternative, which is that we have more than 1 in 10 defectives. So null hypothesis is that theta is less than 0.1. The alternative is that theta is bigger than 0.1. Now, this is typically how you'd see it written in the real world. Kind of for a mathematical sake, you should be able to think about what is theta naught, big theta naught, and what is theta A. They're both subsets of this unit interval. So theta naught is going to be from 0 to 0.1, including 0.1. And theta A is going to be from 0.1, not including 0.1, to 1, including 1. So this is the kind of more formal way of writing what theta naught and theta A are. You should, in the back of your mind, have those, but typically people are actually going to write it above. Okay. What are some other examples we can look at? Maybe we want to, we develop a new medicine for blood pressure. So let's say let theta denote the change in blood pressure after taking some medicine. So maybe we test. We want to test a null hypothesis, which is that there's no effect, our blood pressure doesn't change, versus some alternative hypothesis that we do get a change. So H naught, the null hypothesis, is that theta is 0. There's no change in blood pressure after taking the medicine. And theta A is that theta is not, or sorry, HA is that theta is non-zero. There is some change, either positive or negative. We don't have a preference there. So here, more formally, the space of all possible parameters is just going to be their real numbers. The null hypothesis, the theta naught, the space for our null hypothesis, is just going to be the set containing 0, because that's the only option for theta in that space. And of course, the alternative has to be the difference, so it's everything, every real number except 0. So maybe we can write it like that. It's anything non-zero. So this is kind of a very classic hypothesis test that you could do. So there's some vocabulary here, just practically, that people use. If theta is a one-dimensional parameter, that's really what we're going to be focused on in this course. When the multidimensional stuff is not that much harder and not that much more interesting. So the basic stuff is just for for one-dimensional parameter, then a test of the form 1, if we want to test a null that theta is less than or equal to c versus an alternative that theta is bigger than c, or we could, you could say theta is less than c versus the alternative, which is theta is bigger than or equal to c, or you could reverse these things. Maybe theta is bigger than or equal to c versus the alternative theta less than c, or we can have our last option here. Theta is strictly bigger than c versus the alternative that theta is not strictly less than c. Right? So these are different options. The test of this form is called a one-sided test. And the reason we call it one-sided is we care if, well, why do we call this one-sided? There's a lot of complicated history there, but basically the idea is we care if it's to one side or the other. If we look at our second option, which is maybe that the null is that theta is equal to some value c versus the alternative, which is that theta is not equal to c, or less common but possible, the null is that it's not equal to c versus the alternative is that it is equal to c. That type of test is called a two-sided test. The idea that we don't care if it's bigger or less than this some constant c, we just care that it's not equal to it. And the third kind of class of tests, or vocabulary word here, is that if we look at a hypothesis of the form h naught is that theta is equal to some constant, let's call it c naught, versus the alternative HA is that theta is equal to some constant CA. So here, basically, my space of possibilities, I only have two possibilities, either C naught or CA. This is a quite simple hypothesis, either one value or another. It's not like it's bigger than, it's not like it's not equal to. Each of them only has one alternative, C naught or CA. This is called a simple hypothesis. And of course, being simple, it's going to be where some of the theory starts, because it is the simplest to talk about. You only have two possibilities, and so it's pretty, you can actually do some theory on it without too much trouble. Okay, so that's just some basic vocabulary at this point. Okay, definition. A hypothesis testing procedure is, in words, it is a rule. How you spell rule? That determines which samples, call them x tilde, maybe I say for which samples we prefer the null hypothesis, and correspondingly for which samples x tilde we prefer the alternative. So here's the kind of setup. We have some data. We've collected some data. We assume it comes from some distribution. This distribution has an unknown parameter. We want to do some inference on this parameter. We want to say the parameter is more likely to be here than here. We want to come up with some kind of rigorous procedure to say, is my parameter in this part of the space? versus this part of the space. We want to test a hypothesis on it. So we come up with what's called a hypothesis testing procedure. And we're going to take this sample, and we're going to scrutinize the sample, and we're going to say either I accept my null or I reject my null, one of the two. And all that is some rule that says for these samples, if my samples end up in this region, that's not really going to be consistent with my null hypothesis. Or if my samples end up in this region, that is consistent with my null hypothesis. And so you can accept or reject that null based on whether or not my samples seem to support that null or don't support that null. But at the end of the day, a hypothesis testing procedure is purely some rule that says for these samples, that doesn't support this hypothesis, this null hypothesis, and for these samples, it does support this null hypothesis. So a hypothesis testing procedure, very much like a statistic, the definition of a statistic is not very complicated. It's basically some function of our data. Maybe it can't depend on our parameter. Okay. So there's lots of different statistics you can come up with. Some of them good, some of them bad. We spend a lot of time talking about how do you come up with a good statistic. How do you come up with a good estimator of data? And similarly, for hypothesis testing, the definition of a hypothesis testing procedure is not actually that restrictive. It's just some rule that says, in these cases, I'm going to favor the null. In these cases, I'm not going to favor the null. The hard question, or harder question, is what's a good hypothesis test? What's a bad hypothesis testing procedure? Is there a general thing I can do to come up with a good hypothesis testing procedure, or is it kind of bespoke to each problem? So if we let's say, scripty x here be the support of possible values of x tilde. So x tilde is my vector of that containing my random sample, right? So typically, say, X is some subset, if not the whole space, of an n-dimensional space. So I observe some X's, they live in some n-dimensional space. It might be more restrictive than that, it might be bigger, it might be different, but basically that's the kind of classic setup is, maybe they all have to be positive, maybe they don't, But let X be the possible space, basically the support of the random variable X tilde, the random vector X tilde. In this case, a hypothesis testing procedure, I'm going to denote hypothesis testing with HT procedure, is simply a rule that partitions or divides this space into two sets. X is A union R. So hypothesis testing procedure purely just divides my space of possible samples that I can observe into a space into kind of this disjoint union of two sets. A is called my accept region. So, and R is called my reject region. Right, and so we're dividing up not the space of thetas, we're dividing up the spaces of possible x's. And the idea is that if my little x ends up, right, so basically I have my space of x, my big space of possible x's here, and we're going to come up with some division of this space. Maybe that's our division, who knows, where A is one part of the partition and R is the other part of my partition. If I observe, I draw a sample and I get some little x tilde, right? In A, I'm going to say null hypothesis seems likely, more likely than the alternative. Alternatively, if I get some little x in the reject region, I'm going to say that null hypothesis doesn't seem to be likely given the fact that I've observed this. So if I get an x over here, null is okay, and if I get an x over here, the null is suspicious. So, and that's basically the game with hypothesis testing procedure, is I'm going to come up with some procedure that divides up my samples. The samples lie here. Yeah, that's consistent with the null hypothesis, with theta being in this value, or this set of values. And if I get it over here in my reject region, I'm going to say, that's suspicious, because if theta were in this region, if theta were these values in my null hypothesis, I wouldn't really expect to get an x over there. And so it's suspicious that I'm getting that. Maybe the null isn't true. And that's the whole game. So, my definition here was a hypothesis testing procedure. Simply roll that partitions x into this, and we, quote, reject the null hypothesis if our measured, the little sample we collect ends up in, in R, the reject region, and we accept H naught if I observe an X in my accept region. So again, a very broad definition of what a hypothesis testing procedure is. Doesn't seem particularly related to what we think of as a hypothesis testing procedure. Normally for a hypothesis testing procedure, we calculate some statistic, we compare it to some reference distribution, and we see if it's, the p-value is less than 0.05 or whatever. That's what you think of it. And indeed, many hypothesis tests can be written that way. Of course, you can come up with your own, just arbitrary hypothesis testing procedure. It's probably going to be an awful procedure. As long as you divide up your space, say accept here, reject here, technically that's a procedure. It's going to be a bad procedure. So we'll talk about how to make a good procedure. But oftentimes, we can define R, or equivalently define A, through what is known as a test statistic, which I think we're all a bit familiar with, so that our hypothesis test is basically, we can define, say, A or R, they're complements, right? Say we can define A, where A is going to be the set of X's. Suppose I should use little x here. The set of X's such that T of X is in some set C. So we call T our test statistic. And we call C our critical region. So the alternative way to do it, instead of explicitly defining A and R, is we're going to define a statistic. And if the statistic ends up in some critical region, then we're going to say accept. Or if it doesn't end up in this critical region, we'll say reject. I guess typically people say the critical region is for R. It doesn't really matter. Let's say that's our definition of R. Critical region typically is a reject. So alternatively, it doesn't really matter. You could define A. In this case, A would be defined as those X's where T of X is not in my critical region. Complementary. So maybe a picture is informative here. We have our space X, and then we have some statistics. So maybe this is like Rn, for example. And we have some function, or what we call a statistic, T, and T takes us into another space. Maybe T takes us into the real line. For example, so T is going to map from Rn down to the real line. And we're going to have some critical region. this C here is a subset of R, typically. Right? So maybe my critical region is this. This is my critical region C. And what I'll do is, if I observe some little x, what I'm going to do is I'm going to map it over to this real line through t, so we get t of little x. And if t of little x is outside my critical region, I'm going to say accept my null hypothesis. Alternatively, if I measure some little x and I map it with t, and I end up with some t of x in my critical region, I'm going to say reject. And if you were to do this for all possible x's, you would exactly develop what your accept and reject region are. So in this case, I think our accept region is over here, and our reject region might be over there. So this is an alternative way of doing the same thing. You aren't explicitly defining A and R, but you are defining them implicitly through a test statistic, and you're testing if that statistic is in some region. And typically, as with most statistics we've looked at, they're one-dimensional statistics. They map into the real line. So maybe you test if my statistic is bigger than some number or smaller than some number, or in some region or something. And but implicitly in the background, you could define, as we did here, if your procedure kind of practically, as I get x, I calculate t of x, and I see if it's in C or not. But practically behind the scenes, that implicitly defines an accept region and a reject region. So everything's good. This does cover the kind of classic situation that we're used to, where you calculate the statistic and you look and see if it's in some region or not. So for example here, maybe t is x bar and my critical region is, say, the set from z to infinity. And then my hypothesis testing procedure says I'm going to accept when x bar, or accept for those x's where x bar is bigger than z, and is that what I say? I think I should do this backwards. It should be reject if x bar is bigger than z, and I'm going to accept if for those x's where x bar is less than or equal to z. Right. And that looks like kind of a classic test that we'd be used to. Okay, so some more vocabulary. We're kind of building up a vocabulary of hypothesis testing. So we have a definition of what's called a test function. And typically this is noted with phi. The test function phi is simply going to be the indicator of whether or not we accept or reject for our point. So phi of x, let's say, is well, the quickest way to write it, and you can write it either way. Let's say like this: phi of x is the indicator that x is in in the reject region. The test function is purely the indicator that my sample ends up in this reject region. So this is, of course, 1 if x is in my reject region, and 0 if x is not in my reject region. So it's 1, it's the indicator of if I reject h naught, and it's 0 if I kind of accept h naught. The indicator of rejecting h naught. Notice here that if I look at the expected value of phi of x, so now I'm using the bold x, this is random. So if I imagine I'm drawing a random sample and I plug it in to phi, and I look at the expected value of my test function, the expected value of an indicator, and I think I've said this several times now, but I'll say it once more, the expected value of the indicator that a random variable is in a set A is just the probability that x is in that set A. So in our case, the expected value of this test function is the expected value of the indicator that x is in the reject region, which is the probability that x is in my reject region. So this test function can be useful sometimes kind of notationally, and it is just the indicator of whether or not we reject. The expected value of this thing is the probability that we end up rejecting. And we're going to be interested in this probability that we end up rejecting. This is going to be something that we're very interested in. So let's review a intrastats definition and kick it up a notch. Type 1 and type 2 errors. So type 1 and type 2 errors are related to the probability that we accept or reject our null hypothesis, and hence that expected value of that test function. So let's make a little table of the situations in which we might find ourselves. Okay, there are basically 4 possibilities here. We can either accept the null hypothesis, we can reject the null hypothesis. So accepting the null hypothesis says that x is in A. Rejecting would be that x is in R, our reject region. And underlying, we assume that there's some truth. Either we assume that the null is true, that null being true is that our theta lives in whatever space of parameters theta not, or it could be that the null is false, which is equivalent to saying the alternative is true, which is that theta is in our space, our alternative space of possible theta parameters. So these are our 2 by 2 table. We can accept or reject based on our sample, and it might be, have we done this correctly or incorrectly, the null may be true or not. Now, if the null is true and I accept the null hypothesis, that is a correct decision. Excellent. That's the correct thing to do. Null is true, and we say the null is true. Our hypothesis test says that. If the null is false and we reject the null, that is also a correct decision. The null is not true, and our hypothesis testing procedure says, I don't think the null is true. Great. So that seems to be the correct decision. And then we have our off-diagonal cases. If the null is true, it's possible that we say, I think the null is false. So it's possible that our procedure is either bad or we get unlucky. There's some probability that even when the null is true, we're going to make the wrong decision. So this is a wrong decision up here, and this is called a type 1 error. It's basically incorrectly rejecting the null hypothesis. It's actually true, but we say it's not. Or our hypothesis testing procedure gives evidence that it is not true. The other kind of error, which is called a type 2 error, is if the null is false, but we say, actually, I think it's true. Now, our goal when coming up with a hypothesis testing procedure is to, let's say, create a hypothesis testing procedure that minimizes type 1 and 2 error probabilities. So there's going to be, depending on the procedure and the underlying distribution and what the true value of the parameter is, there's going to be some probability that we make a type 1 or type 2 error. And our goal with hypothesis testing is that ideally you would drive those both to 0. So you'd always accept when it's true and reject when it's false. Obviously, that's not going to be possible because we have probabilistic happenings here, and we're not going to be able to be certain about anything. But we're going to talk about how do we create a procedure that minimizes making these errors. Now, in an intro stats course, you would assign these nice little Greek letters. You call 1 alpha and 2 beta. And you'd say, they tend to be in opposition. So it tends to be true, which is true, that if I make my type 1 error small, it tends to increase my type 2 error. Or if I try to come up with a procedure that pushes my type 2 down, I end up with a higher type 1. So they tend to move in opposition, but not always. And there'll be kind of one of the concerns we're going to have is, can we get our cake and eat it too? All right. Unfortunately, unlike they tell you in intro stats, the probability of making either of these two errors is not a fixed number. Not only does it depend on what the underlying data distribution is, depends on the procedure, obviously. It also depends on what the true parameter is. What is theta actually? And it will depend. If theta is one value, my probabilities will be something different than if theta is another value. So the kind of correct adult way to talk about this, the probabilities of type 1 and type 2 error, is through what's called a power function. So for any theta in our total space of possible thetas, the power function, which is denoted beta, is defined as beta theta is the expected value, and it's going to depend on what theta is, depend on what the true value of theta is. So I'll put a little theta there to remind us that. The expected value of our test function. And of course, we know that this is equal to the probability that I reject my null hypothesis. And I'm going to put a little theta here just to remind us that this probability depends on what the true value of theta is. So one thing versus another thing, this will change. So in intro stats, you, I think, presumably would call beta the power. You would say the power of this test is beta. And the power, as they defined it, was the probability of correctly rejecting. So I'm going to kind of it would basically be this, this lower right box, where if the null is false, I correctly say it's false. That's called the power of a test. In intro stats, people would say the power is beta, and we call it beta, and the probability of type 1 error is they call alpha. And they pretended like they didn't depend on what the true parameter is. Unfortunately, we know too much, and it does depend on what the true parameter is. And so power function more generally is just for any theta. It's just the probability we reject. Let me actually write that down. If we have a true value of theta, this is the probability we reject. Now, that might be a good thing to do, might be a bad thing to do. If theta really is in our null hypothesis, or consistent with our null hypothesis, that's a bad thing to do. If theta is consistent with our alternative hypothesis, that's the correct thing to do. So let's just write that out in words. For if theta is consistent with our null hypothesis, so theta is in our null, theta not, then the probability that I make, that is our hypothesis testing procedure, makes a type 1 error, which is, again, I hate the phrases type 1, type 2. It's very confusing. It's not descriptive. It's basically rejecting H naught when the null is true, when theta is and theta not. So if theta is and theta not, then the probability I make a type 1 error is beta of theta, which is the probability, given that true theta, that my x ends up in my reject region. So if I knew my theta were actually consistent with the null, it's in theta not, the probability I make a type 1 error, given that particular value of theta, is beta of theta. It's the probability that I reject. It's the probability it's truly in the null hypothesis, but I reject. Okay? If theta is alternatively in the alternative hypothesis, or theta is consistent with the alternative hypothesis, then the probability of a type 2 error is, maybe I should just remind you what a type 2 error is. Type 2 error is I accept the null hypothesis when I shouldn't, when it's really in the alternative, or really consistent with the alternative. So if theta is the alternative, the probability I make a type 2 error is the probability, right? So what's the type 2 error? The type 2 error, if really the alternative were correct, the error would be to accept the null. It would be the probability x is an A, which is 1 minus the probability that x is in the reject region, which we know is 1 minus beta of theta. Again, I'm going to put some little subscripts theta to remind us that these depend on theta. So beta theta comes up in a couple ways. It is directly the probability of making a type 1 error, and the null is true. And if the alternative were true, then this would be, then 1 minus beta of theta is the probability of a type 2 error. But you notice that these depend on the true value of theta. And it's not just as simple to say the power of a test is this, the probability of type 1 error is this. No, it depends. What is the actual value? What is the actual true underlying value of our parameter? So let's look at an example of this. Example. Let's assume that I have x1, let's just say we have 5 observations, and these are going to be IID from a Bernoulli distribution with an unknown parameter p. And my hypothesis here is that my null is that I can say p is less than or equal to 1/2, and I'm going to test that against the alternative, which is p is bigger than 1/2. Now, this is kind of a real classic setup for a problem. It's a little bit vague on exactly what's going on, because you do have to be careful that you have to specify everything correctly, all the spaces correctly. Now, implicitly here, I'm saying that the space of possible values for P is the whole unit interval. The null hypothesis consists of 0 to 1/2, including 1/2, and the alternative hypothesis consists of 1/2 to 1, excluding 1/2, but including 1. So this is kind of the more technically correct way to write this, but this is the way you actually see it in practice. It's possible you could have some other weird cases where you don't want to test over the whole unit intervals. You can come up with other things, but kind of implicitly in this problem, this is the kind of most reasonable setup. Okay, so let's just back up here. So what we have is Bernoulli data, right? Coin flips, heads, tails, 0, 1. And I collect 5 coin flips. And I don't know if these things are weighted coins or not, right? So it's possible it's a fair coin, or it's possible it ends up on 0, let's say tails, more often than not, or ends up on heads more often than not. I want to test my null hypothesis is that it's going to that the P, this probability, is less than 1/2. And I want to see, I'm going to collect and see from my data, do I have evidence to show that this thing is more than 1/2, that this probability is more than 1/2? And so if you were to just do this by hand, just come up with a procedure, one thing is you might say is, well, if I get all 1s, I do, all heads, flip, 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 all heads, or all 1s. That seems like the probability would be bigger than 1/2. And so, I need a test here to test this hypothesis. And to specify a test, all I actually have to do is specify the reject region. And so reject region being, if I observe that, I'm going to say that it should be, I should reject the null and favor the alternative. So certainly, if I see 1, 2, 3, 4, 5 1s, I'm going to say I should reject the null and favor the alternative. If I see 5 1s in a row, my suspicion is if you see 5 coin flips in a row and they're all heads, my suspicion would be that the probability is weighted towards bigger than 1/2. All right. So here, that's a test. That's literally all you need to do to specify the test, is just tell me for which observations am I rejecting my null. And that's a test. Maybe not the best test. We'll talk about that. But that's a test. And we can even define this in terms of a test statistic. If I would let T be my test statistic, be the sum from 1 to 5 of my xn's, then what's my reject region? My reject region is just the set of x's such that T of x is equal to 5. All right? If I sum up all these things is equal to 5, that's, I get 5 1s if and only if the sum of them is 5, right? So my reject region alternatively could be written in terms of a test statistic T, and my critical region C would just be the number 5, right? And I'm going to say I reject if T of x is in my critical region, and T of x is 5, and I accept otherwise. So those are equivalent ways of specifying that test. And we can ask for this test what the power function is. What's my power function for this test? So beta of theta, we said, is the expected value of our test function. Expected value of our test function. Or alternatively, you can think about it as just the probability that we reject. Now, T, and you could call this thing T of X, is just a sum of 5 Bernoulli. And we know that the sum of independent Bernoulli, we said these things are independent, is going to be binomial. So the sum of these 5 Bernoulli gives us a binomial with n is equal to 5 and the probability parameter p. So the probability that we reject for our test, of course, is, say, either x is in R or t is in my critical region. Of course, that's really kind of overkill because all I'm saying is this probability t is equal to 5, right? And we know is that this thing, this t, is binomial 5p. And so I can actually calculate this thing, right? It's a binomial. What's the binomial? PDF. It's 5, choose 5, times p to the 5, 1 minus p to the 5 minus 5. That should be, if I plug in my binomial PDF, that should be what I get, which of course is just p to the 5th. Right? It's the probability that all of them are 1s. First one's 1, second one's 1, third one's 1, fourth one's 1, fifth one's 1, right? So if they're independent, we can multiply those probabilities, p probability of each, p to the 5th. So that is my power function. Of course, my parameter in this case is not theta, so maybe I should write this in terms of p. So maybe that would make us feel better here, because this is weird to write it as beta of theta. Maybe we call it beta of p. Doesn't really matter. So beta of p is p to the 5th. And what does this thing look like? So it's just p to the 5th. P goes 0 to 1. And if I split my interval in half at 1/2, this first part of this thing is theta naught, and the second part of this thing is theta a. Right? And my beta, my power function, beta of p, is p to the 5th, so it's something like that, something like that. And I could ask some questions of my power function. The power function tells me a lot about my test. Maybe what is the maximum probability I make a type 1 error? Right? So let's back up here. A type 1 error, right? Scroll back up here. Type 1 error is the probability I reject the null when it's actually true. And we said that is beta of theta. Now, it depends, as I've said, on what the true value of theta is. So if I just ask, what's the probability I make a type 1 error? Say, well, for what value of theta? But I could ask what the maximum probability is that they make a type 1 error. That probably will have an answer. And so what's, let me just write this down. Beta of theta, let me say if theta is consistent with my null hypothesis, beta of theta is the probability of making a type 1 error. And what's the maximum probability I make a type 1 error? So what I really want to do is look at the maximum over theta, and consistent with my null hypothesis of beta of theta. Of course, this is p. We're in my null hypothesis if p is less than or equal to 1/2, right? So we could write it like this, kind of more consistent with the notation of the problem. And so it's the maximum value of beta of p when p is less than 1/2. So it's basically, right, it's this first region here. Oops, not that region, this region here. And clearly, we can look and see the maximum value of beta occurs at 1/2, right? That's because this is monotonically increasing, where you get the maximum value at 1/2. So this thing is going to be beta of 1/2. And we actually know what beta is, right? Beta of p is p to the 5th. So this should be 1/2 to the 5th, which is 1/32. So the first question, which is what's the max probability of making type 1 error? 1/32. Now, in an intro stats class, when they talk about alpha is the probability of type 1 error. Really what they're referring to is the maximum value of a type 1 error. We'll get to that. And the maximum obviously won't depend on the particular underlying value. It'll depend on what the space is, what the null hypothesis is, but it'll be the maximum over that. So you can get just a single number if I ask what the maximum is. So you can kind of get what you want by looking at the maximum here. I could alternatively ask about type 2 error. Of a type 2 error. What's the maximum probability of type 2 error? Type 2 error is the opposite. It's when the null is false, but I accept the null. So if my parameter is in the alternative, that is the null is not true, the parameter is consistent with the alternative, 1 minus beta of theta, we said, is this probability of type 2. So the question we're asking now is we want to find the maximum value over theta consistent with the alternative of 1 minus beta of theta, which is the probability of my type 2 error. In our problem, the alternative is when p is bigger than 1/2, and 1 minus beta of theta. And so we can kind of just, I guess beta of p, right? If we go back up to our picture, so if this is beta of p, let's actually redraw it, right? So let's just do a real quick sketch here, right? This is beta of p goes 0 to 1, 1/2 here. Now for the alternative, we're in basically the second part of the region here. And that's beta of p, so 1 minus beta of p will kind of look like that. And we want to find the value in this interval 1/2 to 1 that maximizes 1 minus beta of p. And so that's going to be basically at 1/2, or we can't go below 1/2 because we have to be in the alternative. And the value that maximizes is going to be at 1/2. So this is going to be equal 1 minus beta of 1/2, which is what it would be, 31/32. So in this problem, they're nicely kind of complementary probabilities. So that's kind of the basics of power functions, and they can tell you a lot about your test because they're going to tell us about, and ultimately we're going to bound these type 1 and type 2 errors in various ways, because what we want to do is come up with a test that kind of minimizes both as much as possible. And so we're really going to be interested in using this power function to try to bound these things. Okay. Let's do this again for a slightly more complicated example. Similar kind of setup. So we'll continue our setup, but consider a different test. And our test is going to have a reject region. Before, our test was when the reject region was all those x's where t of x was equal to 5. Now I'm just going to say where t of x is greater than or equal to 3. Okay. So if you recall what our hypothesis testing was, our test was H0. We wanted to test the hypothesis of p is less than or equal to 1/2 versus HA, which is P is bigger than 1/2, right? So if kind of by layman's, if you were to just say, well, in my sample of 5 points, if I have more than 3 out of the 5, I'm going to say it's bigger than 1/2. If I have less than 35, I'll say it's less than 1/2. That seems like a more reasonable test, but rather than only rejecting when you see all 5 ones. And so this is an alternative test, probably a better test. Makes certainly more intuitive sense that this is a test we would use. And we can ask the same questions, although it's a little more complicated because this region is a little more complicated. It's not just one number now. So in this case, our power function, beta p, as always, is the probability that we reject. And which in this case, the probability that t is bigger than or equal to 3. And so we could write that as the probability t is 3 plus the probability that t is 4 plus the probability that t is 5, right? Because there are only 5 possible or 6 possible values for t, 0, 1, 2, 3, 4, 5. And we know from before that t has a binomial distribution, 5p. And so we could calculate what these are. We have our formula for the binomial PMF. Probability that binomial 5p is 3 would be 5 choose 3, p cubed, 1 minus p squared, plus the probability is 4 is 5 choose 4, p to the 4th, 1 minus p to the 1st power. And then we did this one before, it's just p to the 5th. For the probability t is 5. Algebra, which I'm not going to do, you can write this as p cubed by 6p squared minus 15p plus 10. Okay, right? So it's some polynomial. In p, frankly, it's not that interesting, it's just an algebra problem. You could simplify it to that. And we could ask kind of similar questions as last time. So for example, here's a question. For this test, what is the maximum probability of a type 1 or 2 error? Testing the same hypothesis, we just have a different test. And so hopefully, if we come up with a better test, we can reduce both the probability of these errors. So things to notice about this, if we look at derivative of our power function with respect to beta, derivative of power function with respect to p, so d beta dp, this is a nice little Calc 1 problem. Let me do this in our head. So you can do it out. It simplifies actually quite nicely. It's 30p squared by p minus 1. It doesn't really matter. The reason I write it in that form rather than writing it more explicitly is, because if you just look at this and you had to do it, you probably wouldn't come up with 30p squared by p minus 1 squared, right? Nonetheless, you can factor it out this way. And the reason I want to factor it out this way is because it turns out that this thing is always positive. So what does that mean going back to Calc 1? It means that it's an increasing function. So if I were to sketch out, right, this is a pretty complicated polynomial. And if I were to sketch out a picture of my power function, beta p versus p, and so p goes 0 to 1, 1/2 there. This first region is our null, this second region is our alternative. Our power function is some increasing function. I don't know exactly what it is, but it's something increasing. All right. Notice that power function has to be bounded by 1 at some point, so I don't know exactly what it's going to be, but it has to be between 0 and 1 because it's a probability at the end of the day. It might not ever achieve 0 or 1 exactly, but it's bounded by that. And it's some increasing function, so it vaguely looks something like that. And so basically, if we wanted to, we can play that same game we played in the previous problem. It all actually goes through, because all we really needed in that previous problem was that the power function was increasing, right? When we found our maximum probabilities, all we needed was that beta of p is increasing, and so 1 minus beta of p is decreasing. And so basically the same game can be played if I look at, let's say, max type 1 error. So I want to maximize over p type 1 is if the null is true, so p is less than or equal to half, and I want to maximize the probability of rejecting, which is beta of p. Again, because this thing is increasing, all we need is beta is increasing, and this is going to be maximized at 1/2, so this is going to be beta of 1/2. And if similarly, I could look at the maximum of a type 2 error. So here I'd be maximizing over, now in my alternative, p is bigger than 1/2, and I'm maximizing 1 minus beta of p. And by the same game we played last time, this is 1 minus beta of 1/2. So you see that they actually, 1/2 is the worst value for the test. If I'm at 1/2, which makes sense, right? If I'm trying to decide whether or not it's less than 1/2 or bigger than 1/2, and it's exactly at that border, that's going to be really difficult to determine, even if I have a ton of data. If it's slightly bigger than 1/2 or slightly less than 1/2, right? So if you're really close to that border there, it's going to be really hard to determine. And you can see that maximum is my type 1 error and my type 2 error. So it's kind of the worst possible case. Right, if my true probability is like 0, I'm just going to get a bunch of zeros, and it's going to be obvious that the probability is less than 1/2. If the true probability is like 1 or close to 1, I'm going to get a bunch of 1s, so it's going to be obvious that it's really bigger than 1/2. And the hard part is if it's kind of in between, really close to 1/2, or somewhere like that, it's kind of optimally the worst spot here. And you can see that mathematically it maximizes the probability of type 1 and type 2, right? Alternatively, if I were at, if my probability of close to 0, I'd have a really low probability of a type 1 error, correspondingly high type 2 error probability. And if I were really close to 1, I would have a really low type 2 error probability, but a high type 1 probability, which again makes sense. So that's some nice little examples of kind of the power function and why it's important. And what I'm going to close on here today, because we're just at about time, is I'm going to define the size and level of a test. So we say a test, a hypothesis test, is, quote, size alpha. So alpha is some number, let's say between 0 and 1, if basically the maximum type run probability is alpha. Right, so if alpha is the maximum overall theta in my null of beta theta, this is the maximum type 1 error probability. It's as bad as it possibly could get. And we say a test is level alpha, because sometimes it's hard, that's supposed to read level. Let's try writing legibly. Is level alpha, and again, alpha is some number, some probability between 0 and 1, if alpha, well, let's write it this way, if the maximum type 1 error probability is less than or equal to alpha. So this is max type 1 probability. So ideally, we'd be able to find a size alpha test. So let me back up here. So typically, the classic way that hypothesis test is taught is that we're interested in bounding our type 1 error probability. And it's a little bit arbitrary, but typically that's the way it's set up. You could bound the type 2 error probability and just switch your hypothesis, you give it the same thing, but it doesn't really matter. The point is that typically what we do is we're going to bound our type 1 probability, and then we're going to try to minimize, given our bound on our type 1 probability, we're going to try to minimize the type 2. And sometimes you could say, well, okay, among all size alpha tests, I want to find the test that has the minimum type 2 error probability, or the maximum power is the alternative way of thinking about it. Sometimes it's hard to find a test with exactly an alpha size. So you could relax that a little and say, well, I'm just going to bound it. I'm going to say it's not more than alpha. And then basically what we're going to do is we're going to search and find the best test among all those if I've bounded it. Okay. So this should be fairly reminiscent. We'll talk about more of this more next time. This should be fairly reminiscent of UMBUEs. We're interested in finding the best estimator. It turns out, well, if you let everything be totally unrestricted, there's no answer. And that's the same thing if you're with hypothesis testing. If you let all possible tests, there's not going to be kind of a general, uniformly best answer. And so one way we get around this is we're gonna consider classes of tests where we're fixing the size or the level at a certain number. Okay, but we're at time here, so that's kind of the first introduction to hypothesis testing. And next time we're going to start talking about how do we actually practically build up these tests and how can we connect that back to our estimation procedures that we've developed in the course.